Hi everyone, I'm Luca Piccolboni from Columbia University, and I'm going to talk about CRYLOGGER, a dynamic tool to detect cryptographic misuses in Android applications. Before moving on, let me thank the other authors of this work, Giuseppe, Luca, and Sima. Android applications use cryptographic libraries to perform operations such as encryption, hashing, and authentication. Unfortunately, using these libraries is very complicated. We need an understanding of cryptography to know which algorithms and which parameters to use in a given situation. Suppose, for example, that an application has to perform an encryption with AES. The application has to call an API by passing as parameters the plain text and encryption key in order to obtain the corresponding ciphertext. In addition to these parameters, the application has to specify many other parameters, such as the operation mode or the PADI scheme used for encryption. These parameters are not as easy to configure. Choosing the correct values for these parameters is, however, critical for security. When these parameters are misconfigured, we say that the corresponding cryptographic APIs have been misused. Cryptographic misuses are very common in Android applications. According to some recent studies, almost 90% of the Android applications make at least one mistake in using cryptographic APIs. The good news is that cryptographic misuses can be detected with automatic tools. Most of these tools are static. They analyze the code of the applications to detect where wrong parameters are passed to the APIs. A static tool takes as input the application and a list of cryptographic rules. An example of rule is forbidding the use of the operation mode ECB or electronic code book, when multiple blocks of data are encrypted with AES. Once the tool has analyzed the application, it reports a list of violations. These violations have to be treated as security warnings. A rule violation doesn't necessarily lead to an exploit. It is instead a warning that needs to be further analyzed to make sure there are no problems for the application or its users. Let's see now some examples of rules. Some rules forbid the use of specific configurations of the cryptographic algorithms. For example, Rule 2 forbids the use of broken encryption algorithms, such as DES. Another example is Rule 20, that forbids the use of RSA without padding. Other rules don't let applications use bad keys or initialization vectors. For example, Rule 7 says that we cannot use a static initialization vector. For instance, using 0 as initialization vector with the CBC or cipher block chaining mode makes the data vulnerable to certain attacks. Other rules focus on random number generation. For example, Rule 17 says that we cannot use unsafe random number generators. An example is Java util random, that shouldn't be used for cryptographic purposes. Other rules focus on passwords that are used for key derivation or for storing sensitive data. For example, these rules prohibit the use of weak passwords, blacklisted passwords, or the reuse of the same password multiple times. Other rules focus on key derivation and related parameters. The typical example is Rule 13, that says that we can't use less than 1,000 iterations to generate a key. Using a lower number of iterations is considered unsafe. Finally, some rules are for HTTPS and certificates. An example is Rule 22 that prohibits the use of HTTP. To check these rules, we developed CRYLOGGER, a tool that detects cryptographic misuses by using a dynamic approach. The execution of CRYLOGGER consists of two steps. First, we run the Android application. To do that, we use Monkey. Monkey is a tool that generates random events that trigger actions on the graphical interface of the application. An app developer can, of course, use more sophisticated tests to improve the coverage. We used Monkey because it was the easiest way to execute several apps of the Google Play Store, and we were able to detect many misuses. To log the information about the crypto APIs, we ran the application with instrumented Java classes. We instrumented, for example, the class cipher, the class message digest, and others. In this way, every time one of the functions of these classes is called, we can log the most important parameters that are passed. For example, on the left, you can see that an application uses the class cipher to perform symmetric encryptions. When the function init is called, we store in a log file information about the algorithm, the operation mode, the PADI scheme, and other relevant parameters. The second step is done offline. Once we finish to execute the application, we analyze the log file and report all the violations. The first step is the instrumentation of the relevant Java libraries and methods. We instrumented 12 Java classes that belong to the Java Cryptography Extension, GCE, and the Java Cryptography Architecture, GCA. These classes provide a common interface for cryptographic algorithms to all applications. This interface is implemented by providers, which are crypto libraries, for example, Bouncy Castle or OpenSSL. By instrumenting these classes, we can monitor the parameters used by thousands of Android applications. An example of class that we instrumented is Message Digest. This class implements crypto hash functions. These functions take as input an arbitrary amount of data and produce hash values called digests. We instrumented the method digest so that we can log which particular algorithm is used to calculate the hash, for example, SHA-1 or SHA-256. We instrumented the other Java classes in a similar way by determining the relevant functions and parameters for each class. After we collected the log file, we need to analyze it and see if it violates some rules. To do that, we define 4 checking procedures. Each of these procedures takes as input the log file that we collected and reports a list of violations. The first checking procedure is used to extract from the log all the values of a parameter or a combination of parameters and verify that they can be used for a certain API. All the values that are collected from the log are sent to a rule-specific function that says yes if the values are allowed by the rule or no otherwise. For example, to ensure that we don't use any broken algorithm for symmetric encryption, we check that those algorithms are never used by the application. If we see one in the log, we report a violation. As another example, to check that we don't use weak passwords, we collect all the passwords that we find in the log. We evaluate their strength with an open source tool, and we report the violations. The second checking procedure is used to verify if a parameter of an API is constant or not. For instance, we need to ensure that applications do not use static initialization vectors that are hard-coded. To verify the rules in this category, we examine the logs of 2 executions of the same application and check that the values that are found in one of the execution log are not present in the other one and vice versa. The third checking procedure verifies if a set of values is random or not. For rule number 6, for example, we need to guarantee that the application uses encryption keys that have enough randomness. To verify this rule, we collect all the values of the relevant parameter and we check if the values have been generated with a bad method, like Java util random. If they are, we flag a violation. Otherwise, we apply the NIST tests for randomness. If at least one of the tests fails, we flag a violation. Finally, the last checking procedure checks if a value or a combination of values is reused across the same execution of an application. For instance, for rule number 9, we have to ensure that the same pair of key and initialization vector is never used to encrypt different messages. The checking procedure collects all the values from the log and checks if there are duplicates. If there are duplicates, it means that the app has used the same key and initialization vector to encrypt different messages, which should be reported as violation. Let's now discuss some experimental results. We analyzed roughly 1,800 Android applications by using CRYLOGGER on an emulator running Android 9. We downloaded about 2,000 free Android applications from the Google Play Store. These are popular free apps of 33 different categories. We discarded some applications since we did not detect usage of cryptographic APIs, and some as they didn't work on the Android emulator, either because they kept crashing or they required libraries that could not be installed in our environment. We used Monkey to interact with the graphical interface of the applications by using 30,000 random events, which we saw it was a good compromise between running time and violations reported. So here are the results of our analysis. This graph reports the total number of applications that violate the 26 cryptographic rules checked by CRYLOGGER. The x-axis reports the number of the rule, while the y-axis reports the total number of applications that violate that rule. Let's discuss the results for a few rules. A very high number of applications use broken hash algorithms and unsafe random generators. These numbers are very high because they account for secure uses of hash algorithms and random number generators for non-sensitive data. Unfortunately, it is not easy to discriminate the unsafe uses from the safe uses in these situations. Several applications use bad keys and initialization vectors, which are either constant or they don't have enough randomness. Most likely, some of these problems are coming from popular libraries that are used by many applications. Many applications use also bad passwords. Often, these passwords are used to obfuscate the data stored locally on the smartphone. As mentioned before, each rule violation should be treated as a security warning. In fact, a rule violation doesn't necessarily mean that an exploit exists. To understand if these violations correspond to real exploits, we manually analyze 28 applications, and we collected the feedback from the developers of 8 applications and 2 libraries. We discuss now the main lessons that we learned through this process. First, developers are interested in real exploits that have a direct impact on the security of the applications. Some rules define, for example, the minimum size of a key or the minimum number of iterations to use for key derivation. While these are important rules to follow, their security impact on the particular usage can be difficult to determine. Second, sensitive data are sometimes stored by using poor encryption practices, for example, by employing constant passwords or broken algorithms. These are reported as violations, but they are difficult to exploit by an attacker. Of course, it is better to always adopt safe crypto practices, even when certain attacks, like privilege escalation, are considered out of scope. Third, some violations are raised for non-sensitive data. For example, using a random number generator that is not safe for cryptographic use is okay when the values that are generated are not used as keys. Discriminating these and similar situations is very challenging, and some rules, more than others, can suffer of this problem. We compared our approach with CryptoGuard, a state-of-the-art static tool for automatic detection of cryptographic misuses. We observed that static tools and dynamic tools can complement each other. Static tools are great for analyzing a large number of applications, but they can report false positives because they analyze parts of the code that might never be executed. In addition, they can produce false negatives, as in some cases, they clip the explorations to reduce the execution time. On the other hand, a dynamic tool can focus on the code that is actually executed, but it can produce false negatives when the application is not fully explored. It can also produce false positives, for example, when it is difficult to distinguish critical from non-critical contexts. For future work, we recommend combining static and dynamic analysis for more accurate results. The problem of crypto misuses is interesting, and there are static and dynamic approaches that can detect misuses, but there is still work to do to understand the real extent of this problem. First, we need to improve the analysis of the applications. For dynamic tools, this means improving the coverage by using, for example, test generators that try to trigger the execution of specific APIs. In our work, we used Monkey as it was easy to use, but smarter test generators can guarantee better results, especially for applications that require information such as login credentials. Second, we need to improve the accuracy of rule checking. The safety of using a particular parameter for an API depends on the context. For example, a broken hash algorithm can be used to generate unique IDs for non-sensitive data. To distinguish these situations, we can log more information on the usage of certain APIs, or we can exploit static analysis. In this presentation, I talked about CRYLOGGER, a dynamic tool to detect cryptographic misuses. The tool is available on GitHub if you want to check it out. We showed that it is possible to analyze thousands of applications to look for cryptographic misuses, but accuracy must be further improved to avoid false positives, false negatives, and more in general to make the analysis more accurate. We suggest combining static and dynamic approaches, as these have unique advantages that can improve the overall understanding of crypto misuses when combined. Thank you for watching this presentation.